All right, we're at the final phase of Mendel's experimentation, and the last thing that he investigated was this concept of independent assortment. And the idea is that what he was trying to find out is if genes influence each other's inheritance. In other words, in order to do that, he had to look at two genes at the same time. And that means a little bit more of a complex Punnett square. So there are two alleles in each possible gamete and four possible combinations, right? Remember that what's along the top and the side of a Punnett square are possible gametes and the alleles that we have in these possible gametes. Well, now that we're dealing with two genes, that means there are four possible combinations of alleles in each gamete. So that means a 16 square Punnett square. Like always in his experimentation, he started out with pure parents. So he crossed two parents that were pure, well, one parent was pure homozygous recessive for both genes, and the other parent was pure homozygous dominant for both genes. So they were pure for contrasting traits for both characters. And then he predicted that when he did this, that all the offspring would be heterozygous for both genes. In other words, hybrids for both genes. And that's what we now refer to as a dihybrid. So the F1 generation were all the same, just like always, just like when crossing parents and looking at only one gene. Now in this case, they're dihybrids. They're all heterozygous for both genes. That's their genotype, and their phenotype would be dominant for both genes. So in this case, round and yellow. So the fun begins when he went on from the F1 to the F2 generation. In other words, he actually self-pollinated individuals from the F1 generation here and looked at both genes. And that's what we refer to as a dihybrid cross, because we're crossing two dihybrids, two hybrids that are heterozygous for two genes. So a dihybrid cross is between parents both heterozygous for two genes. Both parents are dihybrids. It's a dihybrid cross. And we're going from the F1 generation, which were dihybrids, to the F2 generation. And so this is what Mendel would predict if the genes did not influence each other's inheritance. And that's the whole idea of independent assortment. In other words, if the genes assort independently, they don't influence each other's inheritance, then this is what we would predict in the F2 generation. The opposite of independent assortment is a concept that we call gene linkage. So in other words, if they did not assort independently, then that means that they were linked in some way. They were attached to each other in some way. They influenced each other's inheritance in some way. So if we define independent assortment, it states that during gamete formation, in other words, during gametogenesis, the alleles in one gene segregate and pass to gametes independently of alleles of other genes. So the alleles segregate without influencing each other's segregation. This Punnett square shows what would have happened if the characters that Mendel was working with did not assort independently. In other words, they were linked. If they were 100% linked, if they had to be inherited together, then this is what Mendel expected to see. And we can refer to this as a predominance of parental types. The parental phenotype would have dominated. In other words, the phenotype of the parents, round and yellow. So most of the offspring, 3/4 of the offspring, would have been round and yellow. But that's not what Mendel saw. What Mendel saw supported independent assortment. So when he actually did this experiment and crossed these plants, he saw this result. So the results that he predicted is what he actually saw from his experimental results. And that supported independent assortment. Now, if you count up how many of each phenotype there is, you'll find that they have a ratio of 9 to 3 to 3 to 1. And how we come up with that is we're going to take a look at that on the word problem on the next slide. So you'll get an indication of, but you're welcome to count them up for yourself here. But we're going to take a look at it in more detail on the next slide. So Mendel's results were close to this predicted ratio, Not exactly, because, it's a prediction and we're talking about probability and chance, but they were close, therefore it supported independent assortment. They were close to predicted and far from what would have been predicted if the characters were not assorting independently, or the genes were not assorting independently. And again, Mendel was lucky that the characters that he was working with in pea plants did assort independently, because if they didn't, it would have confused him, and he may not have even come up with this idea of independent assortment, which is now a principle of basic genetics, a law of basic genetics. So here's a word problem that involves a dihybrid cross, and you would just read your way through and pick out the important information and choose the symbols that you want to use, and then write it as a cross, write the parental genotypes as a cross. And what I'm trying to get across to you here is how you go about assigning the genotypes of the gametes along the top and the sides of this 16 square Punnett square. Again, there are 4 possible combinations, and these are the 4 possible combinations of alleles from each parent. So both parents have the same genotype, therefore what's going to be along the top of the Punnett square and along the sides, the possible gametes are going to be the same. So the first thing you do is you match up the first allele of the first character with the first allele of the second character. That's how we get the capital R, capital Y. You match up the first allele of the first character with the second allele of the second character, and that's how we get capital R, lowercase y. Then you go back and match up the second allele of the first character with the first allele of the second character, and that's how we get lowercase r, capital Y. And then the second allele of the first character with the second allele of the second character, and that's how we get 2 lowercase, an R and a Y. Once you have it set up, then of course you can solve it, and yes, it's tedious. There are 16 squares, there are a lot of R's and Y's that you have to write down, and you have to be real careful that you're matching them up properly, the way they come together and form these possible offspring. But once you do that, then you can go and count up the phenotypic ratio. And I'm never going to ask you to do the genotypic ratio. It's not necessary for one thing, and it's way too tedious for another. But there is a particular order to the way that we count up the phenotypic ratio, just like in a monohybrid cross. And so the way you want to list these possible combinations of these characters is dominant, 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 recessive, recessive, dominant, recessive, recessive. So in this case, that's round yellow, both dominant, round green, dominant, recessive, wrinkled yellow, recessive, dominant, and wrinkled green, recessive, recessive. And I've color-coded each one. But the next thing you need to do after you list the possible phenotypes is determine what each of those phenotypes is going to look like genotypically within the possible offspring within the Punnett square. So when it comes to round and yellow, that means both dominant. That means as long as you have a capital R and a capital Y, that's going to show both dominant traits. So it doesn't matter what the other allele is. That's what these blanks are representing. Doesn't matter what the other allele is. And if you go back and you count up all of those, you'll find that there, and I've color-coded them black here, you'll find that there are 9 of them. Same for round green. As long as there's a capital R and 2 lowercase y's, that's going to be round green, right? Doesn't matter what this allele is. And if you go back and count them up, there are 3 of them. Wrinkled yellow, same situation, just the opposite. As long as there's a capital Y and 2 lowercase r's, that's going to be wrinkled yellow, and there are 3 of them. And then wrinkled green, that's both characters are homozygous recessive. That's the most rare result, and that there's only 1 of those. Okay, so 9 to 3 to 3 to 1. In that order, always. Dominant, 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 recessive, recessive, dominant, recessive, recessive. 9 to 3 to 3 to 1. And you can take that to the bank. In other words, just like for a monohybrid cross with a 3 to 1 phenotypic ratio and a 1 to 2 to 1 genotypic ratio, you can remember that. You don't have to do a Punnett square if you are crossing 2 parents that are heterozygous for one gene, it's going to be a 3 to 1 phenotypic ratio and a 1 to 2 to 1 genotypic ratio, as long as we're dealing with complete dominance. And it's the same thing here in a dihybrid cross. As long as you have two parents that are heterozygous for both genes, in other words, they're both dihybrids, then you're going to get a 9 to 3 to 1 phenotypic ratio, as long as we're dealing with complete dominance. So just remember that, and you won't have to do all this. However, if I ask you to show your work, if I give you a problem like this and ask you to show your work, then I expect you to show me all of this. The only thing that it's okay to leave off is this, the explanation for how we set up the Punnett square. All right, so what's the big deal of independent assortment? Well, independent assortment means that there's more variation in populations and species, which you know is important because it's the raw material of natural selection and evolution. Without variation, there's nothing for natural selection to work with. Therefore, there's not going to be evolution and adaptation to a changing environment, like a changing Earth, like climate change. Now, it's true that genes do not always assort independently. Sometimes there is some linkage, and there can be complete linkage and there can be just some linkage, but most genes assort independently, even though they're on the same chromosome. But if they're really close together on the same chromosome, they can be linked. But again, Mendel was lucky that the genes that he dealt with, these 7 characters and 7 genes that he was working with, all assorted independently. Otherwise, he may not have discovered this what we now consider a law of independent assortment. So genes do not assort independently if they're close together on the same chromosome. They're more likely to be inherited together if they are close together on the same chromosome. But even if they are together on the same chromosome, there is a mechanism that operates during meiosis that will separate them from each other and make them appear to assort independently. Even though they're on the same chromosome and you would expect them to be linked and inherited together, there is a mechanism during meiosis that will separate them and cause them to appear to assort independently. And that's known as crossing over. So crossing over, even though genes may be linked, maybe they're close together on the same chromosome and linked to some extent, they still will cross over and appear to assort independently. And we'll be looking at that when we study meiosis. So to sum up here, because we're done with Mendel's experimental design finally, Mendel's results supported the particulate hypothesis, in other words, the gene idea, that there are these discrete particles, genes and alleles, that are passed from parents to offspring, unchanged. The principle of dominance, and recessive, of course, that some alleles dominate over other alleles. Remember, an allele is a form of a gene, so some forms of a gene dominate over other forms of the gene. They mask it, is a good way to think about it. And then the principle of segregation. And when you remember, when you think segregation, think alleles. We're talking about the segregation of alleles during gametogenesis, during meiosis. The alleles separate into separate gametes. Each gamete gets one allele from each gene from each parent. And then finally, the principle of independent assortment. And the best way to think about that is we're talking about independent assortment of genes. Genes assort independent of one another. Again, during meiosis, and especially because of crossing over, they appear to assort independently, even though they're on the same chromosome. So they get separated from being on the same chromosome by the process of crossing over during meiosis. So now you know who Mendel was, how he carried out his experimentation, what his results were, and how he interpreted his results and came up with these laws, and that's why we revere him as the father of genetics.